Have you ever wondered how a computer can take a really messy digital image and just clean it up almost perfectly? Well, it's not some kind of magic. It's actually a set of surprisingly simple rules that can reshape images, one pixel at a time. So let's dive in and see exactly how it's done.
Take a look at this right here. On the left, we've got some scanned text that's all broken and kind of noisy. But on the right, it's perfectly crisp and solid. Now, this transformation, a computer did it automatically. But how? How does it know how to fill in those tiny gaps and thicken the letters without just making a big mess? That is exactly what we're going to break down.
So here's our game plan. First, we're going to get the basic idea behind reshaping images. Then, we'll get our hands on the first tool, called Dilation, which literally lets us grow pixels. After that, we'll start combining tools for some really powerful techniques, see them in action, and then we'll just appreciate how amazing these simple rules really are.
All right, first up, reshaping digital images. Now, the fancy term for this is morphological image processing. It's a huge part of computer vision, and it's all about changing the structure of an image to clean up imperfections and pull out useful info about the shapes inside it.
Okay, let's jump right into our very first and honestly, our most fundamental tool. It's called Dilation. And the concept is incredibly simple. It's all about growing pixels, making the bright parts of an image bigger, thicker, just more solid.
So what is it really? Well, dilation is just an operation that adds pixels to the edges of things. Imagine you've got a white shape on a black background. Dilation is the process that makes that white shape fatter. It's the core tool for building up shapes.
Now here's where it gets really clever. The computer uses this little pattern called a structuring element. Just think of it like a tiny rubber stamp. It slides this stamp over every single pixel in the image, and the rule is just ridiculously simple. If any part of that stamp touches the original shape, then the pixel under the center of the stamp gets turned on in the new picture. That's it. That one rule, applied thousands of times, is the whole trick.
And boom, here's what that looks like in practice. On the left, a pretty thin letter A. We run our dilation rule over it, and on the right, you see the result. Every part of that letter has expanded outwards. It's thicker, it's more solid. The computer has literally grown the shape.
So what's a real-world use for this? Well, you can fix things. Look at this letter O that has a break in it. By dilating the whole image, the edges on each side of that gap just grow towards each other until they touch, sealing that break perfectly.
Dilation is also fantastic for smoothing out rough edges. See the circle on the left? It's all jagged and uneven. But because dilation is all about adding pixels, it naturally fills in those little nooks and crannies, giving us the much smoother, much cleaner circle you see on the right.
Okay, so we've got a handle on dilation, which grows things. And you can probably guess it has an opposite, called erosion, which shrinks them. Now this is where things get really interesting. By combining these two super simple operations, growing and shrinking, we can build much smarter tools called opening and closing. Let's check them out. This is such a key idea. Opening and closing are just clever combinations of what we already know. So opening is easy. First you erode an image, shrinking it, and then you dilate it right back. The effect? It's like sanding off little bumps and breaking thin connections. Closing is the exact opposite. You dilate first, and then you erode. And this is perfect for filling in small cracks and plugging tiny holes.
Let's actually see opening in action. Here's our original image. You see that thin bridge connecting the two main shapes? And those little jagged bits on top? And that tiny little square all by itself on the right? Okay, now look what happens after we apply the opening operation. The bridge is gone. The jagged edges are smooth. The little bit of noise on the side has vanished. It's cleaned up all those small external details.
Now, let's take that exact same original image, but this time we'll apply a closing. Remember, this time we grow first, then shrink. And look at the result. That small horizontal gap in the left shape, filled in. That little black hole inside the right shape, gone. It has perfectly fused the breaks and plugged the internal holes just as promised.
So why does any of this matter in the real world? Well, this noisy fingerprint is a perfect example. It's covered in little speckles and the ridges are all broken up. But by applying a smart sequence of openings and closings, we can get rid of the noise and reconnect those broken ridges. And this isn't just for fingerprints. This is a basic step for any AI that needs to see clearly, from recognizing a face to helping a self-driving car see lane markings on a faded road.
All right, so that leads us right into our next big idea, practical image algorithms. We now have our four main tools, right? Dilation, erosion, opening, and closing.
So now, let's see how we can put them together to do even more complex and really useful stuff.
Using just these building blocks, we can design algorithms for all kinds of advanced things. We can extract the perfect boundary of an object, we can fill in an entire region with color, we can even find the skeleton of a shape. For now, we're going to zoom in on the first two, boundary extraction and region filling.
Extracting the boundary of an object is, well, it's just so elegant. The algorithm is incredibly simple. You take your original shape on the left, then you make a slightly smaller version of it by using erosion. And for the final step, you just subtract that smaller eroded shape from the original. And what are you left with? Just the outer layer of pixels, a perfect outline.
Okay, so finding an outline is pretty cool. But what about the reverse? How can we tell a computer to take an outline like that and fill it in? Kind of like a paint bucket tool, but in a totally controlled way that's guaranteed not to leak.
The process is called region filling. And we start with just two things, the boundary of the shape we want to fill, and a single seed pixel that we place somewhere on the inside. That one little pixel is our starting point.
And here's the core idea. The algorithm just keeps applying dilation to our seed, making it grow. But, and this is the absolute genius of it, it's a conditional dilation. The rule is, the growth can only happen where it's not hitting the boundary. That boundary acts like a solid wall that the growth just cannot cross.
So the computer just repeats that process. Dilate, but stay inside the wall. Dilate again, stay inside the wall. The filled-in area grows step by step, almost like water filling a glass, until it has expanded to touch every single part of the inner boundary. And at that point, it can't grow anymore, and we're left with a perfectly filled shape.
And that really brings us to the big takeaway here. From fixing broken text, to cleaning up fingerprints, to intelligently filling in complex shapes, every single thing we've seen comes from applying just a few incredibly simple rules over and over again.
So let's do a quick recap with this little cheat sheet. Dilation expands pixels. That's for thickening things and filling tiny gaps. Erosion shrinks pixels. That's for thinning things and removing noise. Opening, that's erode then dilate, is for smoothing things out and breaking thin connections. And finally, closing, dilate then erode, is for fusing breaks and plugging holes. These four operations, they're like the basic grammar of shape for a computer. You know, this is one of the most beautiful ideas in all of computing. Incredible complexity emerging from pure simplicity. By teaching a computer a few basic rules about how pixels can grow and shrink, we give it this powerful new way to see and understand shapes. So I'll leave you with this question. Now that you know these fundamental rules of shape, what other simple rules could we teach our computers to unlock totally new ways of seeing our world?